David Thomas again. I won't go through the introduction of Mistral, as you've seen it once. We are a small business and located in the DC metro area. So the author of the vehicle-based maintenance, the CBM for electronic bodied mounted components, is Shai. Unfortunately, he can't be here. He's in Israel. He wasn't able to make the trip due to circumstances beyond his control. Several of his colleagues made it, but he was unable to. So as he is the author, I'll do my best with the presentation. So the Prognostic health use monitoring system. We're integrators. The company here is Plasan, their Vetronics division, located in the northern part of Israel. We specialize in collecting, fusing, and reading data. And here we see to look to optimize this data, and that optimization, we look to increase safety, preventing casualties due to perhaps to human error, reduces system malfunctions. We have a smart power grid that we normally install with our Vetronic suite. And of course, moving down provides the prognostic hums for diagnostics to include condition-based maintenance. Voila. So here we see, we'll take a look at the components used for the app. And this is what we produce here. They're applications. Just like you load them on your smartphone, we produce appliques for a variety of control vehicles in Israel. This particular one for condition-based maintenance I'm going to be talking about today, but as the same basic layers throughout the vehicle. The vehicle system layer, which is the automotive layer, suspension, brakes, RPMs, and the other automotive functions which come through our CAN bus. We have the tactical systems or tactical sensors layer. Those are power, 360 situational awareness, perhaps video, almost always remote weapon stations and radar on our vehicles. The Vetronic suite you'll see on the left-hand side. Excuse me, the video hasn't come quite over, excuse me, the slide hasn't produced all the way on the left-hand side as it's seeing on my screen, so I apologize there. The ground vehicle architecture Vetronic suite is shown on the left-hand side, and there that includes power, data networking, orientation, crew stations, media, the hull, and of course our V-Box suite. So here is a very simplified diagram. We typically use NATO or NATO GVA standard enabling middleware, where we have continuous monitoring of the vehicle and sensor performance. So here you see we host third-party applications, some of which I've mentioned. And then once we've retrieved that data, we log it, of course, and store it. This is handy for the logistics folks to download and see how the vehicle performed. But we also pay attention to the information real time. So while we will load the parameters of the said sensor or said function, as we start to reach the outside or the outskirts of those parameters, we start additional cautions and perhaps even transmitting this information back to the depot at a suitable time. And it runs on an open architecture. So we have a hypervisor in there, VMware, vehicle machine interface software, so we can interface and use Microsoft, Linux, and so on. Whatever operating system your sensor would come in with. So once again, we'll take the sensor from the automotive, we'll take the sensors from the tactical suite, and then we have the algorithms, and we fuse those different sensors to produce the qualification or end result to measure that condition-based maintenance. Schematically shown there in the top, the control units. There you've got some of the third parties, the mast in this case, crew station, etc. The application protocol, in this case, typically proprietary. And then you've got the transport or the physical layer, Ethernet, CAN bus, RS-232, etc. All this information through the gate comes down through into the data distribution service, the DDS bus, and as you can see on the lower portion of the screen we have the CAN bus, and then coming in there we fuse that. That DDS is a very common networking middleware, just simplifies the fairly complex programming that takes place, offering commands to the nodes. So, condition-based maintenance. So I've set the stage in so much as the typical architecture that we set up in the vehicle, allowing for data retrieval, which is our secret sauce, shall we say. And we're writing the algorithm because most electronic body-mounted devices currently fail as a result of environmental conditions and operational usage. So we're looking at a dynamic statistical CBM approach requiring continuous data collection of real-time situational awareness parameters. So the prognostics of the HUMS principles. Prediction of the remaining service life of these components is becoming a technical area of interest. I don't recall seeing any requirements, and I'm on the lookout for them. There's been gaps identified recently at the industry day out at NATC. I think we had the gentleman from CASCOM, Don Overton, gave us a couple of gaps that he sees. One of those was prognostics and diagnostics for the FMTV. So real-time data acquisition regarding critical vehicle components and performance and functionality. Sophistication in the prognosis is based on the changes in the readings. When the algorithm sees that and detects the numbers while still in the parameters but starts to exceed a predetermined, a preloaded acceptable range, perhaps we start then monitoring with increased intensity. Again, this data is logged, and while you may set parameters based on manufacturers' recommendations, as you log more time under different conditions, and this is the key here, it's not just time and temperature. I mean, you have combat conditions, peacetime training conditions, and as these sensors and sees this different performance, it can provide you with a far more accurate logistics chain. Here's a very simple example of a fuel pump. Here you see the fuel pump condition. It's got low functionality is predicted, an alert is executed, and fuel pump alert for fuel pump number 2. Now that alert could go to the driver, commander, could go to both, could go to neither. Maybe you don't want to trouble them with the fact that that fuel pump has reached this particular condition at this point, but it's going to be interesting back when you get to the depot and the logistics guys take a look at it. Now, if this fuel pump reaches its next condition, it may well need reporting to the driver and commander. I apologize for the small scale on the right-hand side, but logically, a technical problem is identified during built-in test. Prognostic application calculates according to a predefined matching profile. This matching profile, again, could be typically started by manufacturing guidelines and then refined further as you log this particular component over particular terrain and circumstances. So, risk assessment principles, benefits of implementation of the vehicle system that currently is predictive software with a precision of about 90%. It requires choosing appropriate statistical models which suit the risk assessment. And that risk assessment is performed in 2 stages. First, the system situation is recognized as with the matching profile definition, which is updated offline according to accumulated knowledge, as I've explained. And then there's and then it is analyzed to identify whether the value of each tracked parameter is within permitted standard deviation. Recognizing a system at high risk. For convenience and simplicity, my colleague assumed that the decrease in performance of systems and devices due to aging and use of each of the tracked parameters is subjected to the normal distribution. We also assumed that a system should be considered in high risk with regards to the matching profile and should be replaced if one of the tracked parameters exceeds one of those standard deviations. So, in summary, we've written the algorithms, we collect the data, process the data. We haven't completed it as an app, but we have performed all the necessary analysis and most of the software to produce the results. And once again, we have a booth in the South Hall, booth 932, if you'd like to come by, and I can take contact information if you'd like to speak further with the author and exchange notes, etc. So thank you very much, and I'm open for questions, sir.
So Dave, quick question for you on a potential application. How difficult is this to apply to a system? You showed a sample system that you'd been developing the work on, but let's say I have a piece of equipment that otherwise is just a dumb piece of equipment. What would it take to get it employed?
Well, the parameters given to us to generate the first one was that we had to produce a box, a system that could be placed on an existing processor. Depending on the amount of sensors you require and the amount of information you're looking for, you can update a legacy system relatively inexpensively. Implementation of the system is quite easy. Most of it depends upon whether the vehicle was originally designed with any of these sensors involved. Most of you listening to this presentation probably have quite a lot of these sensors on your automobile. You have icons that come up if you've got a flat tire, and so on. So depending on the age of the vehicle will be dependent upon the implementation.
And does the software application, is it flexible enough to be able to be excuse me, used for aircraft or ground vehicles, for example?
Ah, thank you very much. I neglected to say that. That was a good question. Yes, it's platform agnostic, without a doubt. It's currently on a similar, smaller version system is on a small UAV in Israel and being tested. It isn't the principal reason for the test, but we took the opportunity of loading it on there to see how it performed, and that was our SIL, shall we say, our system integration lab when we first wrote the algorithm. Thank you.
Questions?
Thank you very much for your time and patience, ladies and gentlemen.
Thanks, Dave.